Hello. Today we're going to talk about, continue our discussion with bases and focus on bases for Rn, bases for subspaces coming from spanning sets, and some other properties. And this is material from 4.2 and 4.3. So recall from last time, a basis for a subspace, let's say H, is a collection of vectors, let's say B, let's say it's B1 through BP, satisfying two important properties. So the first is that B is a linearly independent set. All right, so we talked about what that meant last time. The only way to make the zero vector as a linear combination of these given vectors is the trivial way. And then the other property is that H equals the span of B. So what that means is that every vector in H can be written as a linear combination of these vectors here, these given basis vectors. And the way I like to think about these two properties of a basis is that they kind of are a give and take, right? So this first condition is saying that there's no redundancy. Remember, a set is linearly dependent means that one of the vectors can be written as a linear combination of the others. In some sense, you didn't need one of them, at least in terms of the span of that set of vectors. And then this other property that's saying that H is a span of B is somehow there's enough vectors, let's say, to quote unquote make everything in H. So every vector in H can be written as a linear combination of the vectors that you gave me. So this is somehow saying that you have enough vectors in the set. This is saying you have not too many, that there's no redundancy in what you've given me. So what are some examples? So e.g., what about bases for Rn? This is our kind of first important example. Well, recall, if I have a collection, let's say V1 through Vp, if this is a collection of vectors in Rn, well, this will be linearly independent. Now, if we have a collection of vectors in Rn, we can slap them together to make a matrix. And remember, the linear independence means that if I write the matrix A, which is, consisting of these vectors as columns, to say that it's a linearly independent set means that this matrix has a pivot in every column. Remember that? So I need a pivot in every column of this matrix. That's the first condition. Now what is it, the spanning condition? Well, this collection of vectors spans Rn, as you know, if and only if this matrix A has a pivot in every row. All right, so the independence was pivot in every column, spanning is pivot in every row. So what is that telling us? Well, so if I'm working in Rn, I want to know, do I have a collection of vectors that makes a basis? Well, I want to look at the matrix it forms, and I need to have a pivot in every column and a pivot in every row, which means, well, in particular, it has to be a square matrix, and, well, pivot in every row and column means that it's invertible, right? It's reducible to the identity matrix. So here's the fact that we more or less just proved, is that, let's say, a matrix, I'll call it M, is invertible, let's say n by n, if and only if its columns form a basis for Rn. So this is a two-way street, that if you give me a matrix that's invertible, n by n, square matrix, its columns will form a basis for Rn. And then conversely, if you have a basis for Rn, you can make a matrix out of those and it will be invertible. So that's a nice kind of criteria there. Now, let's look at some other examples. So what's your favorite invertible matrix, right? It's going to be the identity matrix. Remember, a matrix is invertible if and only if it's reducible to the identity. So if you take the identity matrix, remember the identity matrix of size n by n is going to look like, well, it's got 1, 0, 0 in the first column, then 0, 1, 0, and then the last guy is 0, 0, 1, right? That's the identity matrix. So what I said last time is that if you take the columns of this guy, this should give you a basis. So this gives you the standard, what's called the standard basis for Rn. And it consists of, what are the vectors? Well, the first column, right, that's 1, 0, 0, 0. That was called E1. Second column is E2 up through En. Remember, E1 is just the way we write 1, 0, 0, etc. And, why is this the standard basis? Well, this is kind of, I would argue that, this is the way we think about vectors in Rn kind of automatically. So, if you give me a vector v, let's say 2, 1, minus 3, this is a vector in R3, I can write that as 2 times E1 plus 1 times E2 minus 3 times E3, right? So I'm forming every vector in R3 as a linear combination of these three basis vectors, which, like I said, it's kind of how you think of the Cartesian coordinate system. But of course, this is not the only invertible matrix, so if you give me any other one, so suppose, let's let V1 be 3, 0, minus 6, V2 be, I don't know, minus 4, 1, 7, V3 be minus 2, 1, 5. Now, does this form a basis for R3? Does the collection V1, V2, V3 form a basis for R3? That's my question. Well, what do we do? So again, go back to our result here. Our fact says that this will be a basis for R3 if and only if the matrix I get by taking these as columns is invertible. So let's consider the matrix. 3, 0, minus 6, minus 4, 1, 7, minus 2, 1, 5. And what do I want to do? I want to know, is this invertible? In other words, does it reduce the identity? I need to make row operations. So let's see. So I've got a pivot here. I'm going to reduce under that. So 3 minus 4 minus 2. That's 0, 1, 1. Let's see. I'm taking 2 times the first row, adding it to the third row. That's 0. Let's see. 2 times that. So that's minus 1. And then this is going to be 1. Right? 2 times that, right? And this reduces to, well, 3 minus 4 minus 2. 0, 1, 1. I'm using this now as my next pivot. This is 0. I'm going to add the second row to the third. So what do I get? I get, this is echelon form. I've got 3 pivots. That means this thing is invertible. This matrix is invertible, which implies that indeed this is a basis. Yes, it is, since this matrix is invertible. Okay, so a couple of things to notice maybe before we move on is that the bases for Rn, right, in particular better have 3 vectors in them because I need to have an invertible matrix. So I need to have, if you're looking for a basis for Rn, I better have n vectors. Let me just say, note that any basis for Rn must consist of exactly n vectors. And of course, each vector has to be itself having n entries, right? It has to be a vector in Rn. Okay, so I think I'll do one more maybe example, well, maybe a couple examples here. So next thing I want to talk about is, well, let's go back to maybe an abstract vector space, or our favorite one. So let's consider the vector space, let's say Pn, right? So these are polynomials of degree at most n. And the standard basis for this guy, there's a notion of standard basis here, is given by the set of polynomials 1 t squared up through t to the n. So remember, I'm looking at now the vector space of all polynomials of degree at most n, and I want a collection of vectors, right, which means a collection of polynomials that is linearly independent and spans. And again, this is sort of how we think of polynomials of degree at most n, I want to write them as something times a constant plus something times t plus something times t squared up through t to the n, right? So it's almost a tautology to say that this is a basis, because when I write a vector, any vector in Pn has the form, well, something times 1 plus something times t plus something times t squared plus something times t to the n, right? These somethings we call coefficients. Okay, one last example maybe for this lecture here. And this comes from finding a basis for a subspace that's given as the span of a collection of vectors. So now let's let V1 be 0, 2, minus 1, V2 be 2, 2, 0, and V3 be 6, 16, minus 5. And let's let H be given by the span of these three vectors. Okay? So, what's going on here, maybe I'll draw a little cartoon. So I'm living in three-dimensional space here, and I've got three vectors. Right, so see, I have a color here. I can use this. So you've given me three vectors. You've given me, I'm not going to be drawing them to where they precisely should be, but let's say that's V1. Let's say this is V2. And I don't know, let's say this is V3 here. So again, this is more of a cartoon drawing, not drawn to precision. But I've got three vectors in R3, and I'm saying, look at the span of all those three. Now note, I'm just going to tell you that there's a linear dependency here, right? If I look at V3, that's actually equal to, let's see, what is it? Looks like 5V1 plus 3V2. Let's see, right? So if I take this guy's V3, this is 6, 16 minus 5. This equals 5 times 0, 2 minus 1 plus 3 times 2, 2, 0. See if that works out. That looks good, right? 10 plus 6 minus 5, yep. So this is a dependent set, this set here that you gave me. So this set of vectors cannot be a basis, because remember, a basis has to be linearly dependent. So what I see here is that V1, V2, V3 is linearly dependent. In other words, if you look at this picture here, if you look at the span of these three vectors, it's actually sitting inside a plane. So maybe I'll try to draw that this is supposed to be a plane that contains the three vectors. This is H now. So in fact, these three vectors all live in this plane. And so when I'm thinking about a basis for this subspace, I don't need all three of these things. In fact, a basis for H is given by, what I can do is just pop out that vector V3 because I don't need it. So now I have this collection V1, V2. Now this is linearly independent because it's just two vectors and they're clearly not scalar multiples of one another. And it spans, right? So H is actually equal to the span of V1, V2. Because remember, I didn't need V3. It was already in the span of V1 and V2. And the collection V1, V2 is linearly independent. Okay, so I think that's it for now. We'll continue next time with some more properties of bases, and we'll talk about null space and column space of a matrix. That's going to be our next kind of big topic in terms of bases. We'll see you next time.